AP problem. Now this is one of those problems that has to do with molecular geometry, a chapter 9 problem. So I included some extra resources so we could talk intelligently about those concepts. So this says some binary compounds that form between fluorine and various nonmetals are listed in the table above. A student examines the data in the table and poses the following hypothesis: the number of F atoms that will bond to a nonmetal is always equal to 8 minus the number of valence electrons for that nonmetal. Based on the student's hypothesis, what should be the formula for the compound that forms between chlorine and fluorine? So if I'm looking at the student's hypothesis and I have the number 8, there we go, minus the number of valence electrons for chlorine. Chlorine has 7 valence electrons, so that means there should be 1 F. Which means that my formula then should be ClF, and there shouldn't be any numbers besides that there. And that actually follows because we know that chlorine shows up over here in between sulfur and argon. This is where chlorine is, so of course ClF makes sense because it follows the same pattern. Okay, in an attempt to verify the hypothesis, a student researches the fluoride compounds of other halogens and finds the formula ClF3. I hope I've been saying ClF and not CF. All right. Well, you understand. I make mistakes like that all the time. In the box below, draw a complete Lewis electron dot diagram for the molecule ClF3. So the first thing I do is figure out which one is the central atom. Central atom is going to be chlorine for 2 reasons. Number one, it makes more bonds than fluorine does, even though they're in the same 7 valence electron group. It goes fluorine, chlorine, bromine, iodine, acetine. Chlorine does because it's in the 3rd period, which means it opens up a little bit more room to make bonds, so it makes more than fluorine does. Also, chlorine is not as electronegative, and there's only one of chlorine, which tends to be the central atom when there's only one of it. So I put chlorine in the center like this, and I go my 1, 2, 3, 4, 5, 6, 7, and 7, and then I have the one that is not paired. The one electron not paired gets a fluorine, so that's one of the 3. And then what I have to do then is take one of these pairs of electrons, lone pairs, and then I'm going to split them apart separately so that we can have bonds that look like this. Okay, now that is my Lewis dot diagram. Oh, I guess I should include all the valence electrons for chlorine, because for fluorine, because fluorine does have 7 valence electrons. So that's how I do it. I draw the Lewis dot diagram for chlorine, and then I fit fluorine bonds in alongside it. Like I just kind of match them up like that. Now there's another question here. So we get into letter C. It says 2 possible geometric shapes for ClF3 molecule are trigonal planar and T-shaped. The student does some research and learns that the molecule has a dipole moment. This is important here. That's going to help us determine the difference between the trigonal planar and the T-shape. Which of the 2 shapes is consistent with the fact that the ClF3 molecule has a dipole moment? Justify your answer in terms of bond polarity and molecular structure. Okay, now let's go. I'm going to go to, here's where the resources come in. If I'm talking about trigonal bipyramidal, okay, trigonal bipyramidal, an example of that would look something like this. Boron trifluoride. Boron is a nonmetal. It has 3 valence electrons because it's in the 3rd group after zinc. It's right above aluminum, so it's got 3 valence electrons. Now, we would typically, remember when we do this, I make the box around it, and then I start off at one place, then I count 1, 2, 3, and it looks like this, where each of these electrons has a 90-degree angle in between, except for this one, which is 180. Well, that's not exactly what's going on. When there are only 3 valence electrons, that means I have one here, and one here. That means it can bond with a fluorine here, with a fluorine there, and with a fluorine here, giving each one of these bonds 120 degrees between the three of them. Okay, that's important. This is trigonal, I'm sorry, not bipyramidal. This is trigonal planar. No wonder everybody is confused when I talk. So trigonal planar is this right here. Then my example is BF3 because there are only 3 valence electrons on the central atom. So here's what it looks like when we talk about trigonal planar. Trigonal planar looks like, here's one with boron and chloride. Okay, this is the same thing. It's got 3 bonds, and 0 lone pairs of electrons. And it looks like this right here. Okay, the bond angle is 120 for each one of them. Don't worry about the hybrid. We don't have to worry about that. Okay, so what else was there? There's trigonal bipyramidal. Now, what is trigonal bipyramidal? Let's scroll down here till we get to 5. 5 is trigonal bipyramidal. That means that there are 5 either bonds or 5 places where electrons fit outside the central atom. So if we have all 5 bonds, then it looks like this. Now here's the deal. When I say it looks like this, I mean it looks like this. Okay, so this is a 3-dimensional object on a 2-dimensional surface. The B's that are here and here are called axial bonds because they're north and south pole, like the axis that goes through the globe. That means the B's here, here, and here are considered equatorial bonds because they go around the middle of our molecule. So here, in between the equatorial bonds is 120 degrees, in between an equatorial and an axis bond is 90 degrees, and in between the 2 axis bonds would of course be 180 degrees. That means the bond between there and there is 180. Now let me get rid of some of this stuff so it doesn't look quite so confusing. Now look what happens when we take away, well first of all let me go back to this last thing here and say now that's trigonal planar, so this is trigonal bipyramidal. Okay, trigonal bipyramidal is what we have when we talk about chlorine like this, and it has, so we have one here. Why does that do that? Yeah, I don't know. Okay, one bond here, one bond here with fluorine, another bond here with fluorine, and then I have 2 pairs of electrons. This is essentially the same structure that I just drew on the last slide. So this is, now here's what I'm going to do. I'm going to go through and say I got 1, 2, 3, 4, 5 places where there are electrons. Those are electron domains. 3 of them are bonds and 2 are lone pair. So take a look here. 3 are bonds and 2 are lone pair. So what I have is T-shaped. Okay, T-shaped means that I have lone pair here, and then I have bonds for the rest of it. That's where the T-shaped comes from. Okay, so it looks like that. It looks like that. So 5 electron domains, that's what this is saying. This is saying that 3 of them are bonds and 2 are lone pairs. Okay, and there's my example, ClF3. Okay, so what about, I need to explain about a dipole moment. Take a look at my first example of trigonal planar. Something that is trigonal planar means it has F pooling in 3 different dimensions, or 3 different vectors, like they're going in 3 different directions. So if you were to tie a knot in the middle of the boron and have a rope going this way, have a rope going this way, and have a rope going this way, and had all 3 people the same size and pulling at the same strength, if this molecule doesn't go anywhere, then you have something that has no dipole moment. Okay, no dipole moment. Which means that there's no place on here that is more electronegative than other places because you have equal, like the force of the electronegativity of fluorine is pulling in equal, is pulling equally. Something like HF would of course have a dipole moment. It would be positive at one end and pull towards the negative. So the dipole moment for HF would look like this. The dipole moment for something else, like maybe CH4, where it's CH4, H, 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 except this is a tetrahedral. If they're all pulling in the same direction like this, okay, then there is no dipole moment for these things that are symmetrical. Trigonal planar is symmetrical. T-shaped is not symmetrical, and here's why. On this side here, we get more fluorines and more electronegativity. That means that we have dipole moments flowing in this direction. Okay, so this has a dipole moment. So that means that this ClF3 looks like this and not like that one over there. Not like that one over there. Because this has a dipole moment. Because these lone pairs take away the symmetry of this structure. If there's no symmetry, then you have to have a dipole moment. Okay? That's the deal. All right, I'm going to cut it there and handle the rest of the problem in a second screencast.